Welcome to another lesson of Math 0420 Introductory Algebra. In this video, we will be discussing Section 2.7, Solving Linear Inequalities. In this section, we will graph the solutions of an inequality on a number line. We will use interval notation. We will understand properties used to solve linear inequalities. We will solve linear inequalities. We will identify inequalities with no solution or true for all real numbers, and we will solve problems using linear inequalities. Let's get started. Let's start with a definition. So if we have an inequality, say ax plus b less than or equal to c, then the inequality is a linear inequality in one variable. Solving an inequality is the process of finding the set of numbers or values that make the inequality a true statement. The set of numbers that satisfy the inequality are called the solution set. Let's now talk about graphs of inequalities. So for the next example, we will imagine that we have the inequality x less than 3. So graphs of solutions to linear inequalities are shown on a number line by shading all points representing numbers that are solutions. Square brackets, like these, indicate endpoints that are solutions, while parentheses indicate endpoints that are not solutions. So let's jump right in with our x less than 3 inequality with example 1. Okay, example 1, we want to graph x less than 3. Now this is the set of all numbers, values of x, that are less than 3. So really it's going to be all of the numbers that are from 3 and all the things that are less than that. Now the first question we need to ask is 3 included? And because it's strictly less than, 3 is not included. So how do we denote that on the graph? Well, typically we will denote that with an open circle at that value. Okay? And then we extend the line to the left to include all values of x less than 3. Okay? So that's how we would graph x less than 3. Let's try another example. In example 2, we want to graph all the x values greater than or equal to -1. So in this case, we're going to start at -1, and we want all of the numbers that are bigger than, greater than, or equal to -1. So first question we ask, is -1 included? And the answer is yes, because we have greater than or equal to. So we'll put a filled in circle, oops, not at 1, but at -1. And then we will extend to all the things that are greater than our -1. Again, notice the graph includes -1. Well, what would happen if we had an inequality that involved two different numbers? Let's try that in an example. Okay, so example 3, we want to graph -1 less than x less than or equal to 3. Now this has two separate numbers in it, and what it really means is that our x is greater than -1 and our x is less than or equal to 3. So what that means is that x is between -1 and 3. So to graph that, we know that it has to be greater than -1, but not including -1, and it has to be less than or equal to 3. And then all the values in between there are also included. So when we have less than or equal to or greater than or equal to, when those are used, we use brackets and filled in circles. Either one of those can be used on a graph. And when less than or greater than are used, we use parentheses and open circles. So far, we've only looked at graphing specific examples of an inequality. Well, what if we wanted to represent the solution set of an inequality in a different way? The way we do that is called interval notation. And we'll go back and look at the examples we've done so far and write their solution sets in interval notation. Okay, interval notation. Again, let's think back to example 1. There's example 1 with its graph. And what we know is that these numbers, the entire solution set, represent an interval on the number line. The solution set for this inequality can be expressed in interval notation as from negative infinity to 3. Now you may be wondering, where does the negative infinity come from? Well, the negative infinity comes from the fact that we're extending to the left indefinitely. So I'll write that out. The solution set extends indefinitely left. And then for the 3, we notice that 3 is not included because we have a parenthesis. The right end point with a parenthesis indicates 3 is not included in the solution set. Okay, so if it extends to the left indefinitely, there's an arrow there, that means that we're going to have a negative infinity. Likewise, if it had been the other way and it extended to the right, it would have been a positive infinity. Now, when you're doing interval notation, negative infinity always has to be on the left, and positive infinity always has to be on the right. You can't have infinity to the left and then a number. That won't work. Okay, let's try the other examples in interval notation. Can we write the other examples in interval notation? Example 2 was x greater than or equal to negative 1. So remember back to that graph, the farthest number to the left was negative 1 and it was included, so we use a bracket, negative 1, and then it extended to the right indefinitely, so we use an infinity. Here's another point of note. Anytime we use an infinity symbol, either negative or positive, we always use a parenthesis and not a bracket. Okay, for example 3, we had negative 1 less than x less than or equal to 3. And negative 1, the left endpoint, was not included, so we use a parenthesis. And we use a 3 with a bracket because the right endpoint was included. Okay, let's now break down any possible real numbers a and b and what that inequality, graph, interval notation, and another type of notation would look like. Okay, let's talk about this chart a little bit. Solution sets of real numbers. So if we let a and b be real numbers, then we can talk about the inequality x greater than a. In interval notation, the left-hand endpoint is a, and it goes on toward infinity. Notice that we have parentheses around this because we have a strictly greater than. On new notation, set builder notation, we use curly braces here and here to put the set inside, and this is the set of all x's such that x is greater than a. We just repeat this inequality inside the set builder notation. In the graph, we start with the point A. Notice we have a parenthesis here, and it extends indefinitely to the right. The only difference between that and greater than or equal to in the next row is that we have a bracket here instead of a parenthesis. Same thing for our set builder and for our graph. The only difference is the bracket. On the other hand, if we have x less than a number, like x less than b, our farthest right point is b, and it extends indefinitely to the left to negative infinity. Set builder notation, we just again put the inequality inside. And for the graph, notice we have a parenthesis and it extends to the left indefinitely. Only difference between that and our final row is the less than or equal to, which changes this parenthesis here to a bracket to indicate that the right endpoint is included. Set builder notation includes the inequality, x such that x is less than or equal to b, and then our graph, again, starts at the point b, including b, and it extends indefinitely to the left toward negative infinity. Let's try another example. Example number 4. We want to express the solution set of the inequality x greater than or equal to 0 in interval notation. So the first thing we want to do is ask which case we're in. We're in a greater than or equal to case, which means that the point 0 is going to be our left-hand endpoint if we were to go back into the chart that we had on the last slide. Now, again, what this means is that our left-hand endpoint includes 0, so we use a bracket and 0, and it extends indefinitely to the right, so we go to infinity. And that is the solution set in interval notation. Let's now move on and talk about some properties that are used to solve inequalities. Okay, properties used to solve inequalities. The first is the addition property. Of inequality. And the addition property of inequality says that if A is less than B, then A plus C is less than B plus C for any real number. So if I start out with 2 is less than 3 and I add 1 to both sides of that inequality, then it's still going to be true that 2 plus 1 is less than 3 plus 1. And also, if A is less than B, then if I subtract that number, I'll also retain that same inequality property. The same is true for less than or equal to, greater than, and greater than or equal to. So basically, just like with linear equation or with equations, linear or otherwise, as long as you add the same number or subtract the same number from both sides of the inequality, then you retain the same inequality symbol. That property still holds. Let's now talk about multiplication. The positive, I emphasize positive here, the positive multiplication property of inequality. So if A is less than B and C is positive, in other words, C is greater than 0, then A times C will be less than B times C. So if A is less than B and C is positive, A divided by C is less than B divided by C. So basically, you can multiply or divide both sides of an inequality by a positive real number, and that inequality symbol will still be true. So is 2 divided by 3, is 2 less than 3? The answer is yes. Well, what if I multiplied both sides of the equation by 2? So is 2 times 2 less than 2 times 3? Well, that's 4. and 6, well, 4 is certainly less than 6. So yes, that is true, and that is an example of this property. So the same is true for less than or equal to, greater than, and greater than or equal to. Let's now move on and talk about the negative multiplication property of inequality. So the negative multiplication property of inequality. So if we have that A is less than B and C is negative, that means C is less than 0, then what we have is that A times C is greater than B times C. So what happened there? If we have that A is less than B and C is negative, multiplying by a negative number changes this less than to a greater than. So if you multiply by a negative number on both sides of an inequality, the inequality symbol flips around. So also, if A is less than B and C is negative, then A divided by C is greater than B divided by C. So is 2 less than 3? We've asked that a couple times now. We know that answer is yes. Well, if I multiply both sides of that inequality by a negative 1, then I get negative 2 and negative 3. So what is the relationship between negative 2 and negative 3? Well, negative 2 is greater than negative 3. So that inequality symbol flips. The same is true for less than or equal to, greater than, and greater than or equal to. Let's try some examples. Okay, example 5. We want to solve x plus 6 is less than 9. What can we do to isolate the x by itself? Well, we can subtract 6 from both sides, just like we would with an equation, using the addition property of inequality. And so we're left with x is less than 9 minus 6, which is 3. So that's our final answer there. Let's do another. Example 6. If I want to solve 8x minus 2 greater than or equal to 7x minus 4. Again, the only time we're going to change the direction of our symbol is if we have to divide or multiply by a negative number. We haven't seen that so far, but just reminding you that that might show up. So to get x by itself, the first thing I want to do is add 2 to both sides, and I get 8x is greater than or equal to 7x minus 2. Then I can subtract 7x from both sides, and 8x minus 7x is x, greater than or equal to 7x minus 7x is 0x, and we're left with minus 2. So our solution is x greater than or equal to negative 2. Okay, example 7. We want to solve 1/4 x, redraw that 4. 1/4 x is less than 2. How do I solve? Well, I have 1/4. The way I undo division is by multiplication, so I can multiply both sides of my equation by 4. 4 times 1/4 is just 1, so I have 1x. Again, we didn't multiply or divide by a negative, and 2 times 4 is 8. What if I had wanted to write this particular one in interval notation? Well, it's all the numbers that are less than 8, strictly less than, not including 8. So our right-hand endpoint has a parenthesis, and it extends indefinitely left toward negative infinity. All right. One more example on this slide here. Example 8. We want to solve negative 6x less than 18. How do I get x by itself? Well, the way I do that is by dividing both sides by negative 6. And what happens when I divide by a negative number? Well, that means that my inequality symbol has to change direction. So we know our inequality symbol will go from less than to being greater than. Negative 6x divided by negative 6 is just x, and 18 divided by negative 6 is negative 3. Let's do another example. Example 9. We want to solve 2 times the quantity x minus 3 minus 1 less than or equal to 3 times the quantity x plus 2 minus 14. Well, the first thing we want to do before we start doing operations to both sides of this equation is we want to distribute. So we'll distribute the 2 to the x, and we get 2x, the 2 to the negative 3, and we get negative 6, minus 1, just copying down, 3 times x is 3x, 3 times 2 is positive 6, minus 14. Now we can combine like terms on both sides. 2x minus 6 minus 1 is 2x minus 7. Less than or equal to 3x plus 6 minus 14 is minus 8. And now we're in a position where we can solve it. We can add 8 to both sides to get rid of the 8 on the right-hand side. And we get 2x plus 1 less than or equal to 3x. We can subtract 2x from both sides, and we're left with 1 is less than or equal to 3x minus 2x, which is x. So our final answer is x greater than or equal to 1. Okay. Let's consider one last topic, and that's inequalities that have weird solution sets. Inequalities with weird solution sets. So we want to consider the inequality x greater than x plus 1. Does that strike you as odd to begin with, to say that x is greater than x and then you add something? Something's not quite right here, but what is it? Well, if we subtract x from both sides, we see that we get that 0 is greater than 1. So when is 0 greater than 1? Well, it's not. It's a contradiction. 0 is never greater than 1. So this is never true. So the solution set for an inequality of this type is called the empty set. And the empty set has its own little symbol, which is like a 0 with a line through it, or in set notation, brackets with nothing inside, which signifies there are no solutions. Let's try one more example of an inequality with a weird. Example 10. We want to solve 3 times the quantity x plus 1 greater than or equal to 2x plus 1 plus x. Well, if we distribute on the left-hand side, we get 3 times x, which is 3x, and 3 times 1, which is plus 3, greater than or equal to 2x plus x is 3x plus 1. We can subtract 3x from both sides, and we get that 3 is greater than or equal to 1. So when is 3 greater than or equal to 1? Well, 3 is always greater than 1, so it's certainly always greater than or equal to 1. So it does not matter what value x is, all values of x are in the solution set. So in interval notation, that would be negative infinity to positive infinity, or in set builder notation, it's the set of all x such that x is a real number. Okay, those are a couple of weird cases that can happen. That is the last example of section 2.7, solving linear inequalities. Please let me know if you have any questions as you go through your homework. Good luck on your homework, and I'll see you in the next one.